Albert Einstein, born in 1879 in Germany, was a theoretical physicist who revolutionized the field of physics with his groundbreaking theories. One interesting fact about Einstein is that he was a late bloomer in terms of speech development, not speaking fluently until the age of 4. Despite this, he went on to become one of the most influential scientists in history. Einstein's work on the theory of relativity began with his special theory of relativity, published in 1905. This theory introduced the concept of space-time, where space and time are intertwined in a four-dimensional continuum. It also proposed the principle of relativity, stating that the laws of physics are the same for all observers in uniform motion. One of the key consequences of the special theory of relativity is time dilation, which means that time passes differently for objects in motion relative to each other. For example, a clock on a fast-moving spaceship would tick slower than a stationary clock on Earth. Another fascinating aspect of Einstein's work is the concept of mass-energy equivalence, expressed by the famous equation E equals mc2. This equation shows that mass and energy are interchangeable, leading to the understanding of nuclear reactions and the immense energy released in processes like nuclear fission. Einstein's general theory of relativity, published in 1915, expanded on the special theory by introducing the idea of curved spacetime. According to this theory, massive objects like planets and stars warp the fabric of spacetime, causing the phenomenon of gravity. This revolutionary concept changed our understanding of the universe and paved the way for modern astrophysics and cosmology. Albert Einstein's special theory of relativity, published in 1905, revolutionized our understanding of space and time. One interesting detail about this theory is that it was developed during Einstein's miracle year, where he published 4 groundbreaking papers in physics. The special theory of relativity introduced the concept of space-time, a four-dimensional continuum where the 3 dimensions of space are combined with the dimension of time. This unified view of space-time laid the foundation for modern physics and cosmology. One of the key principles of the special theory of relativity is the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion. This means that there is no absolute frame of reference, and the perception of time and space can vary depending on the observer's motion. Time dilation is a fascinating consequence of the theory, where time passes differently for objects in motion relative to each other. For example, a clock on a fast-moving spaceship would tick slower than a stationary clock on Earth. The formula for time dilation, T equals T bar squart 1 minus V2 bar C equal 2, quantifies this effect, showing how time is dilated as the velocity of an object approaches the speed of light. Another intriguing aspect of the special theory of relativity is length contraction, where objects in motion appear shorter in the direction of motion. This phenomenon is described by the formula L plid L squart 1 is V tour C2, showing how lengths contract as objects move faster. The theory also introduced the concept of mass-energy equivalence, expressed by the famous equation E equals mc2. This equation reveals the profound relationship between mass and energy, showing that mass can be converted into energy and vice versa. The speed of light, denoted by c in the equations, plays a crucial role in the special theory of relativity. The speed of light in a vacuum is approximately 299,792 kilometers per second, a fundamental constant in physics that serves as the cosmic speed limit. Einstein's theory challenged traditional notions of space and time, leading to a paradigm shift in our understanding of the universe. The special theory of relativity laid the groundwork for Einstein's later work on the general theory of relativity, which extended the principles of relativity to include gravity and the curvature of spacetime. The principle of relativity, as proposed by Albert Einstein, revolutionized our understanding of the universe by asserting that the laws of physics are the same for all observers in uniform motion. This principle challenges the traditional notion of absolute space and time, suggesting that there is no privileged frame of reference. One interesting aspect of the principle of relativity is that it implies that there is no experiment that can determine whether an observer is at rest or in uniform motion. This concept fundamentally changed the way we perceive motion and laid the foundation for modern physics. In the context of the special theory of relativity, the principle of relativity led to the development of equations that describe how time and space are perceived differently by observers in relative motion. For example, the time dilation formula T equals T bar square T1 minus V square C squared quantifies how time passes differently for observers moving at different velocities. Another fascinating implication of the principle of relativity is the concept of length contraction, where objects in motion appear shorter in the direction of motion. The formula L prime equals L squared 1 minus V thwart C squared captures this effect, showing how lengths contract as objects move faster. The principle of relativity is a cornerstone of modern physics, with numerous experiments confirming its validity. For instance, the famous Michelson-Morley experiment in 1887 aimed to detect the motion of the Earth through the luminiferous ether, but instead provided evidence for the constancy of the speed of light. This experiment laid the groundwork for Einstein's development of the special theory of relativity and the principle of relativity's central role in shaping our understanding of the cosmos. The concept of spacetime, introduced by Albert Einstein in his special theory of relativity, revolutionized our understanding of the fabric of the universe. Spacetime is a four-dimensional continuum that combines the three dimensions of space with the dimension of time, creating a unified framework for describing the cosmos. One interesting detail about spacetime is that it implies that time is not separate from space, but rather intertwined with it, forming a dynamic and interconnected structure. This concept challenges our intuitive notions of space and time as distinct entities and highlights the intricate relationship between them. In the framework of spacetime, events are described by coordinates that specify both the location in space and the moment in time, providing a comprehensive picture of the universe's unfolding. The mathematical representation of spacetime involves the use of spacetime diagrams, where time is plotted on the vertical axis and space on the horizontal axis, illustrating how objects move through both dimensions simultaneously. Interesting numbers related to spacetime include the speed of light, which is approximately 299,792 kilometers per second in a vacuum, serving as a fundamental constant in the equations of relativity. Another intriguing statistic is the concept of space-time curvature, where the presence of mass and energy warps the fabric of spacetime, leading to the phenomenon of gravity. This curvature is quantified by the Einstein field equations, a set of complex mathematical expressions that describe how matter and energy influence the geometry of spacetime. The concept of spacetime has profound implications for our understanding of the universe, revealing a dynamic and interconnected reality where space and time are not separate but intricately linked in a cosmic dance of motion and change. Time dilation is a fascinating consequence of Einstein's special theory of relativity, where time passes differently for objects in motion relative to each other. One interesting detail is that time dilation has been experimentally confirmed through various studies, including the famous Haffel-Keating experiment in 1971. In this experiment, atomic clocks were flown around the world on commercial airliners, and upon their return, they showed a measurable time difference compared to stationary clocks. This empirical evidence validated Einstein's prediction of time dilation and showcased the practical implications of relativistic effects. Interesting numbers related to time dilation include the formula T equals T var squared 1 minus V2 C2, where T represents the time interval for a stationary observer, T is the time interval for a moving observer, V is the velocity of the moving observer, and C is the speed of light. This formula quantifies how time is dilated as objects approach the speed of light, showing that time slows down for objects in motion relative to a stationary observer. Another intriguing statistic is the time dilation effect observed in high-speed particle accelerators, where particles moving at near light speeds experience time dilation, leading to longer lifetimes than predicted by classical physics. This phenomenon has practical implications for particle physics experiments and underscores the profound impact of relativistic effects on our understanding of the universe. Time dilation challenges our intuitive perception of time as a constant and universal quantity, revealing the dynamic and relative nature of temporal experience in the context of Einstein's theory of relativity. Length contraction is another intriguing consequence of Einstein's special theory of relativity, where objects in motion appear shorter in the direction of motion. This phenomenon challenges our classical understanding of space and reveals the dynamic nature of spatial dimensions in the relativistic framework. An interesting detail about length contraction is that it is a relativistic effect that becomes significant as objects approach the speed of light. As an object accelerates towards the speed of light, its length contracts in the direction of motion, leading to a compressed appearance from the perspective of an observer. The formula L tilde L s squared 1 minus v squared c squared quantifies this effect, where L represents the rest length of the object, L is the contracted length, v is the velocity of the object, and c is the speed of light. This formula demonstrates how lengths shrink as objects move faster, highlighting the dynamic relationship between motion and spatial dimensions in the theory of relativity. An interesting statistic related to length contraction is the observation of this effect in high-speed particle accelerators, where particles traveling at near light speeds experience significant length contraction. This phenomenon has practical implications for particle physics experiments, as the contracted lengths of particles impact their interactions and behaviors in accelerator experiments. Length contraction showcases the profound impact of relativistic effects on our understanding of space and challenges our intuitive perception of spatial dimensions as fixed and absolute. By revealing the dynamic and relative nature of length in motion, Einstein's theory of relativity expands our conception of the universe and the interplay between space, time, and motion. Mass-energy equivalence, as described by Einstein's famous equation E equals mc squared 2, reveals the profound relationship between mass and energy. This equation suggests that mass can be converted into energy and vice versa, highlighting the interconnected nature of matter and energy in the universe. An interesting detail about mass-energy equivalence is that it has practical implications for nuclear reactions, where small amounts of mass are converted into vast amounts of energy. For example, in nuclear fission reactions, a small mass difference results in a significant release of energy, as demonstrated by the atomic bomb and nuclear power plants. Another fascinating aspect of mass-energy equivalence is the role it plays in understanding the energy content of objects. The equation E equals mc2 shows that even a small amount of mass contains a tremendous amount of energy, emphasizing the potential for harnessing this energy in various applications. Interesting numbers related to mass-energy equivalence include the speed of light, denoted by c in the equation. The speed of light in a vacuum is approximately 299,792 kilometers per second, serving as a fundamental constant in physics. This speed plays a crucial role in the conversion of mass to energy, as even a small amount of mass can release a vast amount of energy when multiplied by the square of the speed of light. The concept of mass-energy equivalence revolutionized our understanding of the universe, revealing the dynamic interplay between mass and energy and expanding our comprehension of the fundamental forces at play in the cosmos. Albert Einstein's general theory of relativity, published in 1915, extended the principles of the special theory to include gravity and the curvature of spacetime. One interesting detail about the general theory of relativity is that it proposes that gravity is not a force, but rather a curvature in the fabric of spacetime caused by massive objects. This concept revolutionized our understanding of gravity, presenting it as a geometric effect rather than a traditional force. An intriguing aspect of the general theory of relativity is the prediction of gravitational time dilation, where time passes differently in regions of strong gravitational fields. For example, clocks closer to massive objects like stars tick slower than clocks in regions of weaker gravity, showcasing the impact of gravity on the flow of time. Another fascinating consequence of the theory is the prediction of gravitational lensing, where light bends around massive objects due to the curvature of space-time. This effect has been observed in astronomical observations, confirming Einstein's prediction and providing evidence for the curvature of spacetime by massive objects. Interesting numbers related to the general theory of relativity include the Schwarzschild radius, which defines the size of a black hole based on its mass. The formula for the Schwarzschild radius is Rs equals 2 times g times m divided by c squared, where Rs is the Schwarzschild radius, g is the gravitational constant, m is the mass of the object, and c is the speed of light. This formula illustrates how the mass of an object determines the size of its event horizon, the point of no return for objects falling into a black hole. Another intriguing statistic is the prediction of gravitational waves by the general theory of relativity, where massive accelerating objects create ripples in spacetime that propagate as waves. These gravitational waves were detected for the first time in 2015 by the LIGO Observatory, confirming another aspect of Einstein's theory and opening a new era of gravitational wave astronomy. The general theory of relativity has profound implications for our understanding of the cosmos, revealing the dynamic and interconnected nature of spacetime and gravity. By presenting gravity as a curvature in spacetime, Einstein's theory reshaped our conception of the universe and laid the groundwork for modern astrophysics and cosmology. Curved spacetime, as described by Einstein's general theory of relativity, reveals how massive objects warp the fabric of spacetime, causing the phenomenon of gravity. One interesting detail is that the presence of mass and energy curves spacetime, affecting the motion of objects and the flow of time. An intriguing fact is that the curvature of spacetime is quantified by the Einstein field equations, a set of complex mathematical expressions that describe the relationship between matter and the geometry of spacetime. Interesting numbers related to curved spacetime include the prediction of the Schwarzschild radius, which defines the size of a black hole based on its mass. This formula illustrates how the mass of an object determines the extent of its gravitational influence, shaping the curvature of spacetime around it. An interesting fact is that the general theory of relativity predicts the existence of black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape. The Schwarzschild radius formula calculates the size of a black hole's event horizon based on its mass, illustrating the extreme curvature of spacetime near these cosmic entities. Another intriguing detail is the concept of gravitational waves, ripples in spacetime caused by massive accelerating objects. The detection of gravitational waves in 2015 by the LIGO Observatory confirmed another aspect of Einstein's theory and opened a new era of gravitational wave astronomy. These waves provide a unique way to study the universe and uncover hidden phenomena in the cosmos.